This is exactly how smart contracts are working. First, let's have a look what is a smart contract anyway. The term smart contracts was coined by a computer scientist named Nick Szabo, and this was already in 1994. Essentially, within Ethereum, it's a piece of code that is running directly on the blockchain. It is more like a state machine, and it needs a transaction to change the state. Additionally, the smart contract can do some logic operations. The state change from a smart contract happens always through mining through the transactions. Good to know is also that Ethereum smart contracts are Turing complete. If you are writing a smart contract, you can do it in different high-level languages. There is the most popular one, Solidity. There's Serpent or LLL, and there are other ones. They all compile down to a binary, and the binary contains EVM assembly code. And EVM stands for the Ethereum Virtual Machine. The most popular language right now is Solidity, and this course will also build upon Solidity. It's always compared a little bit to JavaScript. I personally found that it's not really like JavaScript, but because the other languages are more like completely different languages, then Solidity is essentially a little bit like JavaScript. Every high-level language, like Solidity, compiles the code to bytecode, which is essentially Ethereum Virtual Machine assembly code. And every Ethereum node in the network executes the same code, because every node has a copy of the whole blockchain. Now there are other languages. There is, for example, Serpent, which is similar to Python. There is LLL, which is a little bit like low-level Lisp. Then there was Mutant, which is a deprecated Go-based language for Ethereum. And there is also Viper, which is more research-oriented. Here's the structure of a typical Solidity contract. Each contract looks like a class that we know from other languages. It starts with the contract keyword and then a name, and then it has all the functions and all the different other things that a contract can contain. So this is how a contract starts. Then the contract itself can contain functions. It can contain control structures like if, else, and so on. It can contain loops like for, while. It can have different data types. There is the unsigned or signed integers, there's booleans, there's array, structs, mappings, addresses, and many more. Good to know is the current version of Solidity does not support floats. It may come in future versions, but right now floats are not supported. Solidity contracts are inheritable, and there are some special structures like modifiers. Solidity contracts can also import other contract files. On the right side here, you see the typical start of a Solidity contract, which we are going to write later in this course. How do we deploy such a contract? First of all, we need to create a contract. We need to write it. We write it in Solidity, which is very high level. It's like writing JavaScript code. Then this contract gets compiled to bytecode. It's similar to assembler, and it runs on the Ethereum Virtual Machine. Then we send this bytecode to the network. It's a transaction without a receiver and only containing the data. The network then will just deploy the contract and give it an address. Now, once we have the contract deployed, we want to interact with the contract. I'm always interested how this looks on a low-level basis, even though we don't use it. So here's the explanation how you interact with the contract on a very low-level basis. Of course, if you want to interact with the contract, you need to send a transaction. And the transaction in Ethereum can have a data field. And the data field contains the information to the node to interact with the contract with a specific function. And to get the function name, we have to hash the function with the SHA-3 hash. This works like the following example. Let's suppose we have a function, this function, and this has two parameters, a uint variable and a uint other variable, and then the function body. If we want to interact with this function, then we have to send a data field with the SHA-3 hash of this function and then the two parameters, but only the data types. So this is happening internally when you're interacting with a contract. But we are not going to do this because there are better ways now. The client side uses a so-called application binary interface. It contains all the function parameters, return values of the contract. It's used to interact with the contract because the client does not know based on the binary of the contract, how to interact with it. This is how an ABI array, an application binary interface, looks like. Basically, it's a JSON file and it contains all the information to interact with the contract. The smart contract on the blockchain is a binary file. Again, the client software doesn't know the interfaces, so it needs to be told via an external configuration file how to interact with the contract. On the right side here, you see a typical structure of such an ABA file. Once the contract is deployed, how can we change the smart contract? The blockchain is immutable. That means once the data is deployed, you cannot change it. That means once the smart contract is deployed, you cannot change the smart contract. So we have to be very careful when we program them. That means we have to do a lot of testing and then even more testing. We will talk about the workflow a little bit later. But for now, take away, once you deploy the smart contract, you cannot change it. What have you learned in this lesson? Smart contracts are running directly on the blockchain in EVM assembly code. They are executed by every node and they are Turing complete. We will write them in Solidity and they compile to bytecode. They have to be tested extensively and an ABI array is the key to interact with the contracts. Got any questions or suggestions? Head over to the Q&A section. We will answer them regularly. Have any feedback? We would love to hear it. Are you disappointed or have any other questions? Just shoot us a message.